Hey everyone, we're here live. I'm Dave of Professor Dave Explains. Wherever you may be watching me, I'm partnering with Chegg to bring you virtual office hours. So it's just like office hours at your university, but you're online with me. And we're going to be talking about Organic Chemistry 1. So the plan here is to be bringing you these office hours weekly at this time. And we're going to try to follow along with what you're learning throughout the semester in Organic Chemistry 1. So today I have some questions that I prepared for you, but also feel free to send me some questions in the chat, and I will try to I will try to get to as many as I can. But I also have the ones that I prepared here for some of the early stuff, like we're going to talk a little bit about nomenclature and some of the other things that you normally cover in the first couple weeks of OChem 1. So if this is intriguing to you, go ahead and visit the Chegg the Chegg YouTube channel. And they're covering actually multiple different topics. It's not just me. And so there's a whole schedule over there if you want to see what topics are being covered. But I'm over here covering Organic Chemistry 1 for you. And so once again, if you have any questions that you want me to address, if you're studying OChem 1 right now, and I'm seeing some of you guys popping up in the chat, some of you not taking OChem 1 right now, but you're welcome here anyways if you like to get a little bit of review. And so yes, why don't we go ahead and get started? I will keep an eye on the chat. Feel free to keep saying hello, but definitely if you have a burning question about some OChem stuff that you're learning in class, chime in at any time. So I'm going to go over here to the document I have here. So just to get things rolling, this first question: which of the following functional groups does not contain a carbonyl? So remember that in things to understand in organic chemistry, we have to be able to recognize different functional groups. So let's go over these. So this is saying does not contain a carbonyl. So what is a carbonyl? A carbonyl is C double bond O, right? C double bond O, and then there may be two other things on either side. So what are these? We have aldehyde, carboxylic acid, ether, and ester. Okay, so what is an aldehyde? An aldehyde is, it's actually a carbonyl with hydrogen on one side, or technically could be both sides, but at least one hydrogen atom, and then potentially alkyl on the other side. Now let's see what a carboxylic acid is. A carboxylic acid is a carbonyl with OH on one side and then alkyl on the other side, typically. Then what is an ether? An ether is an oxygen atom that necessarily has alkyl on either side. So we would represent that as ROR. So that's what an ether is. And then finally, an ester is carbonyl with OR on one side. So that's similar to carboxylic acid, but instead of a hydrogen after the oxygen, it's more alkyl. So we can clearly see that three of these have a carbonyl. The only one that does not is the ether. So ether would be the answer to this first question. Okay, let's go ahead and take a look at what has been happening in these questions here. Let's see if we've got one. What's the different? Let's see. Okay, so Orion asked something that's a little bit more of a Gen Chem question. So maybe we can we'll skip over that. But I do have Gen Chem tutorials that you can check out. It's actually one of the very first videos. Actually, it's the first video in the Gen Chem playlist. If you need to take a look at that. Proton NMR from Crippled Cockroach. That's going to come a little bit later in the semester. And okay, Lukesh has one about resonance. There is one about resonance in these questions that I have here, but feel free to ask one if you have something very specific. And let's see. Okay. Okay, that's why is it called a carbonyl? I really don't know. Anyway, all right, that's it for now. So let's move on to the next one. So we're going to do a little bit of nomenclature. Definitely nomenclature, IUPAC nomenclature is what most people learn in the first week of OChem 1. So we're definitely going to do a little bit of that. So if we have this question, draw 1-fluoro-2,4-dimethyl-heptane. How are we going to draw that? So the first thing is we notice that we have this prefix hept. Hept means 7, therefore heptane is going to be a fully saturated hydrocarbon, and it's going to be 7 carbons long. So let's go ahead and draw that, 4, 5, 6, 7. So remember, with line notation, every vertex and endpoint is a carbon atom. So we have 1, 2, 3, 4, 5, 6, 7 carbon atoms. Now, the easy part about going from the name to the structure is that you can just go ahead and assign the numbering system as you please. So let's just go ahead and write these out. So there are our 7 carbons in our heptane. And so now we just have to draw the substituents. So it says that there's 1 fluoro. So that means on carbon 1, we have a fluoro group. So let's do that. And so this may be kind of confusing to some students because they see that there's another endpoint here, but that's not a carbon atom, right? This is a bond leading from carbon 1 to a fluorine atom. So this is 1 fluoro. And then we have 2,4-dimethyl. So di means that we have 2 different methyl groups, and 2,4 is telling you which carbons they are on. So here is our methyl on carbon 2, and here is our methyl on carbon 4. And we don't have to do any stereochemistry because it didn't specify whether they're R or S, so we can just draw them flat. We know that that's not the true geometry, but that is going to be just fine. So if you had a quiz with this question, this structure would be totally acceptable, and that would be the answer. Okay, let's check in again real quick. Aldehyde, don't put... Why don't we put the C? The Adawi asks, why don't we put the C and instead 2 lines? So every vertex and endpoint is implied to be a carbon atom. It doesn't mean you can't write the letter C in there. That would still be accurate. But in organic chemistry with line notation, the convention is that all of the carbon atoms are implied. We don't have to write in almost any of the carbon atoms unless they're connected to some other. There are certain functional groups where you would write it in. But in this case, we wouldn't have to do that for a carbonyl. Let's see. No ums channel. I do have pre-planned questions, but you also can ask a question. But we're going to limit this to organic chemistry 1. No other topics. That's what we're working on right now is organic chemistry 1. Okay. Yeah. Okay. Okay. Before we move on, I can address this one. The death by 2. So says, hey, Dave, can you discuss the difference between EZ alkenes versus cis and trans? That's a good question. So I can go ahead and draw this here. If we have an alkene, let's say we have an alkene like this, and let's put a fluorine atom there, a chlorine atom there, a bromine atom there, and a hydroxyl there. So the reason that E and Z nomenclature is absolute configuration. It is the way that we describe this in a rigorous way, whereas cis and trans are relative terms, right? Cis and trans is a way of saying, okay, this bromine and this chlorine are trans to one another. This bromine and this fluorine are cis to one another. But we also need to be able to rigorously name this molecule. And so in order to do that, we have to use the Kahn-Ingold-Prelog convention. So here is one of the carbon atoms. Here is the other carbon atom. These are the 2 carbon atoms participating in the double bond. And we look at the 2 groups that are stemming from each of those carbons and assign them a priority based on atomic number. So here, this carbon is connected to fluorine and chlorine. Chlorine has a higher atomic number than fluorine, so that one takes priority. Then we look at the other carbon. This one is connected to a bromine atom and an oxygen atom. Now, a very important point about Cahn-Ingold-Prelog convention is that we're going one atom at a time. So we're not comparing bromine and the hydroxyl group. We're comparing bromine and the oxygen atom. Here, it doesn't really matter, but imagine if we were comparing two alkyl groups with a lot of branching, then it does become very important. So again, we're comparing one atom at a time. Bromine has a greater atomic number than oxygen, so that one would take priority. And then, so we would call this a we would call this an E alkene because the highest priority groups are on opposite sides of the double bond. So you can imagine a line or a plane cutting through that double bond containing both carbon atoms. And if the high priority groups are on the opposite sides of that line, then that is an E alkene. If they were on the same side, then it would be Z, because Z, Zame, Zide. That's how you're going to remember it. Sounds silly, but it's the easiest way to remember it. Z, Zame, side. But here they are on the opposite sides. So that is going to be an E alkene. So once again, just because you asked about cis and trans are relative terminology. E and Z are absolute. That's an absolute configuration. Let's see. Okay, let me see if I can find another good question here. We're going to get to molecular geometry in a moment. We're going to get to some of that hybridization stuff in a moment. Let's see. Got some flat Earth comments. I appreciate you guys, but this is not the venue for that. Yeah. Okay. Cool. So we're all caught up. So let me move on to the next nomenclature one. So a little bit trickier is going from the structure to the name, right? Because there's a couple additional steps here. And so what we need to do is, the first thing we have to do is identify the longest carbon chain. So the longest carbon chain is going to be, here. So in this case, it's pretty easy. It's just the zigzag that's right there. But you have to be careful. If this alkyl fragment up here had an additional carbon on it, that would be the longest carbon chain. So don't always take it for granted that it's the one in this straightforward zigzag right there. So that's the longest carbon chain. That's step one. Step two is to number the carbons so as to give the first substituent occurring soonest. So we have two ways that we could number this. We could go left to right, or we could go right to left. If we were to number left to right, the first substituent would occur on the second carbon. If we were to number right to left, the first substituent would occur on the third carbon. Second is sooner than third, so we're going to number this left to right because that gives the first substituent occurring soonest. And that's because alkyl and halogen are of equal priority. If we had something like a hydroxyl group, that would actually take higher priority. And so we would only care about that hydroxyl group over alkyl and halogen. But in this case, alkyl and halogen have equal priority. We're going to number so as to give the one that occurs soonest. So now that we have this, we know that we have a hexane, and then we just have to show what substituents we have. So we have a bromo group on carbon 2, and we have an ethyl group on carbon 4. I do see a question. Couldn't it be both of the chains? Aren't they both 6 long? Lux Ray forever. Yes, absolutely. I could have highlighted these two carbons to be in the main chain instead, and it would be identical. And in fact, it's of course identical because the carbon-carbon sigma bond between 3 and 4 is constantly rotating. So these are switching position all the time. So yes, it would be the same chain. Okay, so now we have a bromo on 2, an ethyl on 4. So the next thing we have to do is we have to list the substituents. We list them first, and we list them in alphabetical order, and then the parent chain. So here we have B for bromo before E for ethyl. So we have 2 bromo, 4 ethyl hexane. Okay, so there's a dash between numbers and letters always, so that's why we see these 3 dashes. We're putting 2 bromo first because B for bromo before E for ethyl. then for ethyl, and then hexane, because there are 6 carbons in the chain. So it is a hexane. Okay, let me check back real quick. Both of the chains, yes. A couple of you guys got the name correctly. Why does an atom, okay, so Freak Guy says, why does an atom singly bonded become sp2 hybridized if it has a p orbital adjacent to it? So it will be sp2 hybridized if it has a double bond, right? A carbon could have a double bond to another carbon, and then you have unhybridized p orbitals that are overlapping to create a pi bond. I'm actually going to show an example of that coming up in a moment, so you can see that illustrated. Could you go through some Newman projections? I do have one Newman projection on here, so we will get to that. If it were sp2, I don't think it would be. Seth, yes, I have a whole organic chemistry series that you can watch from the beginning. Okay, so yep, that's it. That's caught up there. So let's move on. Let's do one more nomenclature. So we're going to name this compound. So this time we have a cyclic compound, so it's a little bit different. Now, this one is a little tricky. We have, it's a cyclopentane. We have 5 carbons in the ring, so it's a cyclopentane. And so that part is easy, but now we have to know how to number the substituents. So when we have a cyclic compound, we're going to number the ring so as to give the lowest set of locants possible to the substituents. So for example, if we started down here, we could have this one be carbon 1, and then it could be 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, which would give substituents on carbons 1, 3, and 4. But is that the lowest set of locants possible? It actually isn't. If we were to take one of these carbons, we could have this be 1, 2, 3, 4, 5. So we could have substituents on carbons 1, 2, and 4. So 1, 2, and 4 is lower than 1, 3, and 4. So we're going to go with 1, 2, 4. Now the question is, which way do we go? Do we have the methyl on carbon 1, fluoro on 2 and 4? Or do we have fluoro on 1 and 4 and methyl on 2? So here we're going to do the latter just because fluoro is lower, takes priority in alphabeticity over the methyl. F for fluoro before M for methyl. And so for that reason, we're going to go carbon 1, 2, 3, 4, 5, like that. So that one is a little tricky, right? We might be wondering which one is carbon 1, the methyl or the fluorine. Certainly we know it's going to be 1, 2, 4. But we weren't sure which way we were going to go here. So now we're going to list the fluoro first. So we have 1, 4 difluoro, 2 methyl, and just because this is all one word, but I'm running out of room, so I'm going to jump down here, cyclopentane. So there's commas between numbers, dashes between numbers and letters. And it's F for fluoro first before M for methyl. And then, by the way, just so we are aware, the di does not affect the alphabeticity. So it's not D for difluoro, it's F for fluoro. In this case, it wouldn't have mattered, but there are other instances in which it would, like chloro and dibromo. It's still dibromo before chloro, things like that. So that just is something to be aware of. Okay, let's take a look here. Okay, yep, nothing else here, I think, too pressing. Oh, wait, someone said, the death by 2 said, so if it was an ethyl instead of methyl, it would be 1 for ethyl. Yes, that is correct. It is correct because E for ethyl before F for fluoro. So that would have changed the numbering scheme, and we would have put carbon 1 on the ethyl where the methyl is now. Very good question. Okay. Number 5, draw acetone, which is the common name for propanone, and then state the hybridization of each carbon atom and describe their bond angles. Okay, so let's draw acetone. Let me use blue here. So this is what acetone looks like. Remember prop. So prop means three, and then one means ketone. So propanone, just from reading the word propanone, we know that it is a 3-carbon ketone, which is the smallest ketone that you can have. So there's propanone. Now we want to state the hybridization of each atom. Now, in order to do this, it might be useful to draw in the implied hydrogens because these are two CH3s. So let's draw in the hydrogens. So there are the hydrogens on that one. And there are the hydrogens on this one. Okay, so what can we say here? Let's use some highlighter. So we've got a couple there, and we've got one there. So these ones here are sp3 hybridized. They exhibit tetrahedral electron domain geometry and molecular shape. And they have 109.5 degree angles. Okay, so we can see that if a central atom is bound to 4 electron domains, the farthest away that 4 electron domains can be spread out in 3-dimensional space is going to require adopting a tetrahedral configuration. And so it is going to need an s orbital and 3 p orbitals in order to hybridize them to generate 4 sp3 hybridized orbitals in order to bond with these 4 other atoms, the carbon, the carbonyl carbon, and 3 hydrogen atoms. So that will be tetrahedral, and it'll be 109.5 degree bond angles. And I will say this, in organic chemistry, even though the hydrogen atoms are always implied and there's other shortcuts with line notation, it is going to be tremendously useful for you to be able to visualize this. So when I didn't draw, first I drew propanone, but then I drew in the implied hydrogen atoms, right? You definitely want to be able to do that because there are different aspects about reactivity when we start looking at SN2, SN1 reactions, things like that, it's going to be important to be able to draw in all those atoms and generally be able to visualize the geometry of a molecule in line notation. That's going to be incredibly useful later. Okay, then, so that applies to both of these 2 carbons. Then over here, we have a carbon that is sp2 hybridized. And it is trigonal planar. And it has 120 degree bond angles, right? And so the difference here is that this carbonyl carbon is only bound to 3 electron domains. It's bound to carbon, carbon, and oxygen. It still has 4 bonds, but it's got a double bond to oxygen. So if it's only bound to 3 electron domains, the way that 3 groups spread out the most in space is to make a triangle, a trigonal planar situation with 120 degree bond angles. That's the farthest away that those groups can be. So it is extremely important to be able to look at molecules in line notation and be able to identify the hybridization of each carbon, whether it's sp3, sp2, or sp, because that is going to inform so many things about reactivity, the way that nucleophiles come in, and so forth. So that's super duper important. Let me just make sure everyone's up to speed with this one here. Sorry. Okay, let's see. Luca says, can you explain the degrees again? I always get that part confused. So if you imagine something that's sp hybridized, it only has 2 groups. Here's a central atom and here's 2 groups. The farthest apart they can be is directly opposite each other. So 180 degree bond angles. That's linear geometry. Then sp2, like we just saw with the carbonyl carbon, now we have a central atom and we have 3 groups surrounding it. And those electron clouds are repelling each other, so they spread out and form a trigonal planar situation with 120-degree bond angles. When we introduce a fourth group, now we have a tetrahedral situation. We have 4 groups that are all attached to the central atom. Those are going to spread out into a tetrahedral configuration with 109.5-degree bond angles. Then with 5 and 6 and so on, you get smaller and smaller bond angles because you're packing more groups around the central atom. Let's see. No more. Let's see. Abudi, no IR spectra today. That tends to happen a little bit later in the semester, so we will get to that there. Let's see. Diamond is carbon 4. Carbon NMR. So yeah, no spectroscopy today. We'll get to that a little later. I'll plan for that. Also, because in order to talk about spectroscopy, we really need spectra to look at. So that would be up there. Okay, so let's move on. Draw all of the resonance structures for the nitrate ion NO3-. So let's go ahead. So first of all, we have to be able to draw the Lewis dot structure for the nitrate ion. So we have a central nitrogen atom. Now, this is going to want to have 4 bonds to 3 different oxygen atoms. So we right away figure out that we're going to have a double bond to one of them and then a single bond to the other ones. Now, what we also need to understand is the concept of formal charge here. If we draw in all of the valence electrons for these oxygen atoms, we're quickly going to see that these have negative charges. The ones that have only one bond to the nitrogen have negative charges, and the nitrogen in the center has to have a positive charge. So when you learn about assigning formal charge, there are a lot of different courses and instructors have these very convoluted ways of calculating this. I'm going to tell you the absolute easiest way to assign formal charge. All you need to do is take the normal number of valence electrons for an atom and compare it to the number of electrons that it's contributing to the Lewis dot structure. So nitrogen typically has 5 valence electrons, right? There are 5 valence electrons for nitrogen, but here it is only contributing 4. It is contributing 1 of the electrons in each of the covalent bonds that it is participating in, right? 4 is 1 less than 5. 1 fewer negatively charged particles means it's going to have a formal positive charge. Now, look at these oxygens here. Oxygen typically has 6 valence electrons, right? And again, you can find these on the periodic table. You're just looking at the row that it's in and just counting from the left, right? So oxygen is typically going to have 6 valence electrons, but here it is contributing 7. It is contributing 6 in the form of these 3 lone pairs, and then 1 of the electrons in that covalent bond with nitrogen. 7 is 1 more than the typical valence of 6. 1 more negatively charged particles means a formal negative charge. So that is the case for both of these oxygens. And then up here, this oxygen is neutral because 2 for each lone pair and then 1 for each of the covalent bonds. That's 6. 6 is what we expect, so that's going to be a neutral atom. So, so that's the Lewis structure for the nitrate ion, NO3-. The reason it has a net negative charge is because we have 2 minus charges and 1 plus charge. So +1 and then -2 gives us -1. So that is a -1 charge for the nitrate ion. Now, how are we going to get the other resonance structures? So in order to draw resonance structures, you have to, the only electrons you can move around are pi electrons. So pi electrons are electrons in pi bonds and lone pairs. So in a double bond, we have 1 sigma bond and 1 pi bond. That means the one of those bonds, which is a pi bond, is delocalizable. Resonance is always about moving around delocalized electron density, and that's pi electrons. So why don't we take one of these lone pairs, that negative charge right there? Let's put that. Let's put that right here. So we're going from the lone pair to the middle. You know what? Let me make it even a little more clear that we're going right to the middle of that ON bond. So that arrow ends in the center of that bond, which indicates that we're forming a pi bond. However, nitrogen cannot violate the octet. There's only a couple atoms, there's only a couple elements that follow the octet rule, and nitrogen is one of them. It's not going to be able to accommodate a fifth bond, so it has to lose a bond, which is fine because there's a pi bond over here that can go up to that oxygen up there. So we have just pushed some arrows around that are going to allow us to draw another one of these resonance structures. And this time I won't draw all of the lone pairs. We understand where they are. So this is the result of what we just said. We're saying that this lone pair goes over here to form a pi bond, and then this pi bond goes up here to form an oxyanion. So that's another one of the resonance structures. Now what can we do? Where have we not had a double bond yet? Well, that would be right here. So let's have that go right there, and then we're going to kick that up. So if there are no lone pairs shown, drawing the arrow from the negative charge is what you want to do. A negative charge represents a lone pair. So it's totally fine to draw the arrow. These are electron pushing arrows, by the way. So these are going to be very important when we start looking at mechanisms. So we need to understand that they go from electron rich to electron poor. So we're always starting from electron density. So lone pairs, negative charges, etc. So we can draw this arrow from the negative charge to the center of that ON bond, and then we're going to take another arrow from this pi bond up onto the oxygen, and that is going to allow us to draw the third resonance structure for the nitrate ion, and that looks like this. So those are the three resonance structures. You're typically going to see them in brackets like this with these double-headed arrows separating the resonance structures. Now, it's important to understand that actually none of these exist, right? Individual resonance structures do not exist. What exists is the composite resonance structure, and so that looks like this. And there we have to show delocalized pi electron density all over the regions of the molecule where it is delocalized, which in this case is the entire molecule. So these dashed lines represent partial pi bonds. It's almost like there's 1/3 of a pi bond everywhere. And that's because we're taking these resonance structures and averaging them. And that shows you the true distribution of the electron density. So we use these individual resonance structures in order to write out mechanisms. But it's very important to understand that none of them actually exist. This is what exists: the composite with delocalized pi electron density all over the molecule. Okay, I think we got a bunch of stuff on there. So let me just zoom back a little bit. I'm not sure exactly how far. Let's see. Bin asks, hi, I am confused. What is the difference between structural formula and Lewis structures? So a structural formula would be this, right? NO3 minus. That's a formula. That's a molecular formula, which does not exhibit bonding. It does not display the actual bonding. A Lewis structure or a Lewis dot structure shows you the actual bonding, right? It shows all of the actual covalent bonds between every atom. So they're both very important, both very useful. Sometimes we just write out the molecular formula, but oftentimes, and especially in organic chemistry, we're always going to be writing out we're going to be drawing the in-line notation or the Lewis structures of these molecules so that we can understand what's going on. Let's see. Isn't air only 2 atoms? No, there are many molecules in air. Let's see. What specifically makes that one weeb? What specifically makes resonance structures different from simple rotations of the ion in physical space? So here there's a symmetry, but there are many instances in which it's not a symmetrical molecule. So you could have different functional groups, but there remains different resonance structures, and that is completely delocalized around those portions of the molecule. So here, you're absolutely right that rotating the molecule would give you the what appears to be the different resonance structures, but that's not actually what's happening. Whoops. Okay, let me just make sure I get to the top here. Let's see. Spectroscopy, no, yeah, we're not going to do that yet today. Wow, there's a lot of you guys. Sorry, just a sec. Let me get to the top. Okay, I just got to the top. That's about it. All right, so let's move on to number 7. Draw ethylene, illustrating the relevant hybrid atomic overlap responsible for generating the carbon-carbon bonds. So for ethylene, it's C2H2, right? So here's a carbon atom. Here's a carbon atom. And we're not caring too much about the hydrogen atom, so we'll just draw those bonds there. So C2H2 means that we have a triple bond between the two carbon atoms. So how are we going to display that? And we're going to display that using some orbitals. So first, we're going to take these sp hybridized orbitals. So these are sp hybridized orbitals. So the carbon is sp hybridized. So one sp hybrid orbital is bound to the hydrogen, and one is being used to make the carbon-carbon sigma bond. So this is a sigma bond, and it is this overlap that is generating the sigma bond. So it's a sigma bond because the overlap is on the internuclear axis. So directly between the carbon atoms, there's overlap in between them. So that line that contains that orbital overlap also contains the carbon atoms. So that's what a sigma bond is. Now, because the because the carbon atoms are sp hybridized, remember there's 3 p orbitals per energy level. So if one of the p orbitals is being used to form sp hybridized atomic orbitals, then there are 2 more unhybridized p orbitals per carbon atom. So let's draw p orbitals here. Let me go ahead and erase that. Let's get this out of the way. Let's draw these orbitals here. So here are some p orbitals. Let's use this color. And this lateral overlap is going to generate a pi bond. So this is a pi bond right there. Now, that is one p orbital each. Remember, each p orbital has 2 lobes. So this is one p orbital. And now what we're going to do is we're going to draw the last p orbital for these carbon atoms. This gets a little tricky to display. I'm not the best artist of all time, but if you want to imagine that in 3 dimensions, we're developing this kind of propeller-looking thing. And so let's go ahead and get this orbital overlap. That's what's happening there. And that is another pi bond. So we are understanding that with ethylene, there are 3 bonds. It's a carbon-carbon triple bond, right? So we're saying that there's a sigma, there's direct overlap of sp hybridized orbitals to give the sigma bond, and then there is lateral overlap of unhybridized p orbitals on two different axes to give the pi bonds. So that's what's going on for ethylene, also known as ethyne. Okay, a lot of activity. Let's take a look. No, ethylene is ethyne. Let's see here. Yeah, if you guys want to try to keep it on topic, that would be great. Is H3O plus an electrophile? No, not technically. I mean, the proton is an electrophile, right? It can transfer a proton, but we would not really say that. Let's see. Okay. All right. Number 8, draw the Newman projection that depicts the most stable conformation for the C2C3 bond in butane. So let's see. We've got butane. So let's draw this. And so we're talking about the C2C3 bond. So let's say that we are looking this way and we want to draw the Newman projection that is going to depict that. So let's go ahead and do this. So we have 3 groups connected to the front carbon. So here is the front carbon and here is the back carbon, according to the way that we are looking at this here. So what are the 3 groups? If we're looking directly down this way, we've got a methyl group going straight down. So these ones are going to originate at the center of this circle here. And then we have 2 implied hydrogens that are going to go this way and this way. So that's what's going on the front carbon. Now on the back carbon here, what else do we see? Now these bonds are going to originate at the edge of the circle because what we're indicating is that they are groups that are connected to a carbon that is obscured from our vantage point. So it's like we're looking down this tunnel, we're looking at this carbon is immediately behind it, so we can't really see it, but we can see what it's connected to. So we can see these other groups peeking out. So this methyl here is sticking up from the back carbon. And then we have 2 implied hydrogens. Those would be here and here. So if we needed to, if there were other groups on here, those would be indicated with wedge and dash bonds. But we can also draw in the implied hydrogens. So that would be if we wanted to do that. Now, these could be some other groups, and then those would have to show up in specific spots on the Newman projection. And so that's what a Newman projection is we're looking at the relative configuration of groups on the front carbon versus the back carbon and noticing the dihedral angles here. And so this happens to be the most stable conformation. This is the most stable conformation because the groups that produce the most steric hindrance, in this case the methyl groups over the protons, are as far away from each other as possible. So this is an anti-configuration. So an anti-configuration means they are directly opposite each other. It's a 180-degree angle here. And so this is the anti-configuration. And so by the way, this is why we draw alkanes in zigzag like this, not just for fun, but because it truly is the lowest energy configuration for an alkane. It allows the alkyl chain to continue to be anti on either side as you go. And so just in terms of relative energies, the other possibilities would be you could have a gauche configuration. And so if you had this situation and then you rotated one of the sigma bonds to give the methyls adjacent, so this would be a gauche configuration, and we sometimes denote that with this symbol here. That's a little sloppy. Boom. So that is a gauche configuration because these are adjacent. Okay. So yeah, let's write gauche. So gauche and anti are the 2 possible staggered conformations. Staggered meaning we have these 60-degree dihedral angles. So the groups are all in this. We have one like this and then the other like that. That would be a staggered configuration. What we also could have is eclipsed configurations. So if we had the front carbon like this, and then we had the back carbon like this, let's do the not as bad version first. We'll do that, and we'll put the methyl down here. So this is an eclipsed interaction. And then let's also do the fully eclipsed. So if we have CH3 there, and then we have the CH3 on the back carbon there. So this is a fully eclipsed interaction. We have the two methyl groups exactly on top of each other. So that is the most that's the highest energy configuration. That's the configuration that forces the two most sterically repulsive groups to be as close to each other as possible. So this would be the highest energy. This other slightly better eclipsed configuration would be the next worst. That would be the next highest energy. Then, staggered is always going to be better than eclipsed. So we finish the eclipsed, and then gauche would be next because it is staggered, but the methyls are closer to each other than they need to be. And then this anti-configuration would be the best. That's the lowest energy conformation for that bond in butane. So that's a little bit about the Newman projections. Those are very important to be able to draw. Let me go ahead, and there's a lot of you guys talking here. So let's see. Let's see. That's pretty long. What is it? Ken asks, what is it that makes the anti-configuration stable again? So as we said, we have methyl groups produce more steric hindrance than protons, right? They're bulkier, they're just larger groups. And so there's an energetic premium on putting those groups as far away as possible. It's basically just like the Vesper stuff, the molecular geometry stuff. Those molecular geometries are determined by those groups that are connected to the central atom wanting to get as far away from each other as possible. So the same goes for the Newman projections. The anti-configuration is the one that puts those bulkiest groups as far away from each other as possible. So that would be it. Let's see. JS asks if there was a third CH3, would they be on 120 degrees? So I may know what you mean. Here, let's do this. Let's erase all of this, and let's add another methyl somewhere. So let's say that there's a methyl here. Okay. Now we have another methyl group there. So let's see what the best configuration would be. We're going to do the front carbon just the way we did before. So there's CH3 going down that way. And then now it's important, right? Now we have a methyl going up on the back carbon. And then from that perspective, the dash bond is going down and to our left. The dash bond is going beyond the screen. So from our perspective on that side, it's going to our left. So we're going to put that there. And then there is that carbon. So this is actually also the lowest energy configuration because there are two carbons on the back. There's no way that we're going to get away with no gauche configurations. We're going to get one gauche interactions, I should say. There's going to be one gauche interaction no matter how you twist this, right? If you were to take the back carbon and rotate it, it's either going to be this carbon that's gauche to that one, or this carbon would be rotated over here and would be gauche to that one. Or even worse, you could have both of them gauche. So the worst configuration would have these two methyls in this position, and then you'd have two gauche interactions. So then, in this case, we have three different staggered configurations. The one I guess technically just two. The two gauches and then one gauche or the other gauche. So those other two being energetically identical. So that would be the situation with that. Let's see. Chukwu asks, chiral carbons are sp3 hybridized. Yes, there with almost no counterexample, we are typically saying that if you have a chiral center, so let's say we have something like that. This is going to be a chiral center because it's connected to 4 different groups: the methyl, the ethyl, the hydroxyl, and the implied hydrogen. And so, in order for it to be connected to 4 different groups, it's going to have to be sp3 hybridized. That's why if we have something like a carbonyl carbon is sp2 hybridized, it's not going to be a chiral center. So that is a good question, and that is the answer. So this question here that Chag highlighted: can you do a Newman projection of a cyclohexane? So it's actually going to be essentially exactly the same. It's just basically you have 2 Newman projections. So if you it depends if you have a chair configuration, it's really just 2 Newman projections that are connected at the bottom and the top. So it would take a little while to draw, and we only have 10 minutes left, but it wouldn't be. It's actually not much more complicated than a normal one. Nick asks, what if the 2 CH3 groups eclipsed the front hydrogens? Yeah, so definitely eclipsed would be worse, right? Eclipsed would be, so I think what you're asking is, let's put the front carbon there and the hydrogen there and the hydrogen there, and then now you're saying put the CH3 there and the CH3 there and a hydrogen there. So any eclipsed interaction is going to be higher energy than any of the staggered interactions. This in particular would be the second highest energy configuration. One that would be worse would be if either of these methyls was eclipsing the other methyl. That would be the worst one. But definitely any eclipsed interaction is going to be higher energy than the staggered ones. Ryan asks how to calculate number of stereoisomers of any organic compound. That is going to be 2 to the n, where n is the number of stereocenters in the molecule. I didn't include a bunch of chirality stuff today because that's usually kind of like the second unit. First, you kind of do nomenclature and conformational analysis and stuff like that, and then we get to chirality later. So I'll probably include a bunch of that next week. Okay, caught up. So let's do 2 more real quick. How many constitutional isomers are possible for C5H12? So C5H12, when you have CN, HN plus 2, if it's in that format, this is fully saturated, so we don't have to identify any degrees of saturation. So 1 is obviously going to be straight chain pentane, right? So there's one of our constitutional isomers. Now let's take one of these carbons and stick it in the middle somewhere. So how about this, right? We can take this carbon. We can take this carbon and pop it over there, right? So any constitutional isomers means the same atoms of the same elements, but they can be connected differently. So if you take any atoms and stick them somewhere else in a way that still makes a legitimate structure, that's going to be a different constitutional isomer. Now here we're almost done because there's only one more thing that we can do, and that would be to draw this one. So we can have neopentane, and those are all the ways that we can do this, right? So the answer is 3. Any other? There's no other way to connect these. So the answer is 3. Let's see. Chukwu, I actually explained E and Z a bit earlier, so maybe you didn't catch the beginning of the stream, but this will be posted on my channel, so you can go back in the first 15 minutes or so. I talked about E and Z absolute configuration versus cis and trans relative configuration. That so that was already talked about. Same with Anuar. Yeah, I explained that earlier. So yeah, this will be on my channel. You can go back and look at that live stream. Okay, number 10, draw the most stable conformation of cis 1-tert-butyl-4-methyl cyclohexane. So we have cyclohexane, and we know we're drawing a chair. The chair is the most stable type of conformation for cyclohexane. So we're going to go ahead and draw the chair first. Now, this already gives a lot of students a lot of trouble. And so just to give a few pieces of advice, you want no bonds approaching verticality. We do not want what I call bow tie syndrome. This is a very bad chair because it's not possible to see which is the leftmost or rightmost carbon. We don't want to do that. So what we're doing is we're taking cyclohexane. So imagine a hexagon here, and we're viewing it from the side. Right, we're taking this hexagon and we're going like this and rotating it to its side, and we're looking at it edge on. So this makes it very difficult to do that because we can't really see the orientation properly. So let's get rid of that. So we want a very clear leftmost and rightmost carbon. So you can either draw this one or you can draw that one. It doesn't matter. These are the two possible chairs. So let's stick with this one. Now, for a chair, we have an axial and an equatorial position on each carbon. And so one of these bonds is going to be pointing up, and one of them is going to be pointing down, and one of them is going to be axial, and one is going to be equatorial. So here are all of the bonds here. And what I want you to recognize is that these all are tetrahedral centers, and they're all obeying, they all have sp3 hybridization. They all have 109.5 degree bond angles. So you have to be able to see the little tetrahedron at every carbon. That's going to be very important to be able to visualize. And so this part of the ring is closer to us, and this part of the ring is farther away from us. So it's very important to be able to see, right? It's not a flat molecule. We're looking at this from the edge on. And so the equatorial positions are more energetically favorable than the axial positions. The axial positions are the ones that are going directly up and down. So this is so this is axial, 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 this is axial. Those are the axial positions. And then this is equatorial, 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 this is equatorial. So those are the ones that are not going directly up and down. They're going either slightly up or slightly down at an angle. And those are the more energetically favorable positions, because from those positions, there will not be any diaxial interactions. So diaxial interactions are these. This is a form of steric hindrance. There is a repulsion that occurs between the groups at the axial positions, and we want to avoid that if possible. So when it asks draw the most stable chair conformation of this molecule, we have two substituents to place. 1,4 tells us their spatial arrangement, but then we're going to place them both equatorial because that's how you get the most energetically favorable conformation. So let's put the tert-butyl group on carbon 1. We're going to say arbitrarily that this is carbon 1. So here is our tert, that's a little long. This is our tert-butyl group right there. And then, so if this is carbon 1, then let's go clockwise and go 2, 3, 4, 5, and 6. And so we need to have a methyl on carbon 4. And so let's put that methyl here. So we have our substituents on carbons 1 and 4. They are necessarily going to be trans to one another. So this molecule will be cis. I'm so sorry. I read that wrong. Yeah. Okay. So it's okay because all we have to do is make one little change. We are going to put the methyl here. So it is necessarily cis 1-tert-butyl-4-methyl cyclohexane, and that means that one of them has to be axial and one of them has to be equatorial. There's no other way. If they have this spatial orientation, then if it's cis, they're either both down or both up. So one of them is going to be axial, one is going to be equatorial. The tert-butyl group is the bulkier group, and so it's going to produce the most steric hindrance. So that one, there's a higher premium on putting that one in the equatorial position. So that one has to be equatorial on carbon 1. And then over here, we've got the methyl on carbon 4. And that is going to necessarily be axial. So about 30 seconds. Let me just check if there's any really quick I can answer. Elimination or substitution mechanism. So we're going to get to those. We'll probably do a bunch of chirality stuff next week. And then maybe on the third week, we'll start doing all the SN2, SN1, E2, E1. No favorites. I enjoy them all equally. Yeah, I think that's all the questions. So that is the end of the office hour. Thanks so much for tuning in. Again, I'm going to be doing this with Chegg. I think the intention is to do this every week at this time, and we're going to go follow you through your OChem 1 semester and give you all the help that you can get. So if you are an OChem 1 student, definitely tune in next week. Bring your questions, whatever you have from class. If you're not an OChem student, totally still feel free to tune in. If you could, try to keep the commentary to a minimum, because it makes it more difficult to find the legitimate questions. I know you love the flat earth content and all that stuff, but that's not what we're doing right now. So feel free to watch along, but try to be respectful of the people who are here trying to learn OChem. So check out the Chegg YouTube channel if you want to see the schedule of the different subjects that there are office hours for. There might be another subject that you need help in for class. Otherwise, I will see you next week again at this time. I believe it will be again 4 p.m. Pacific, 7 p.m. Eastern next Tuesday for more OChem help.